Welcome to the class. In this video, we envisage to discuss Claisen-Schmidt condensation. Claisen-Schmidt condensation is a base catalyzed mixed aldol condensation between an aromatic aldehyde with no alpha hydrogen atom and an aliphatic aldehyde with at least one alpha hydrogen atom to yield an alpha beta unsaturated aldehyde, or it is a base catalyzed mixed aldol condensation between an aromatic aldehyde with no alpha hydrogen atom and a methyl ketone to yield an alpha beta unsaturated ketone. A methyl ketone is a ketone in which one side of the carbonyl group has been flanked by a CH3 group. The reason as to why this is referred to as the aldol condensation here, even though the intermediate formed is a ketone and the product formed is an alpha beta unsaturated ketone, is simply because the mechanism of this reaction is same as that of aldol condensation. And the reason as to why both are referred here as mixed aldol is because the product formed here is an adduct of the two substrates. The substrate belonging to the aromatic group and the substrate that belongs to the aliphatic group. The reason as to why it is a condensation is because of the elimination of a very simple molecule of water. To understand the two comments better, let us go through the reaction. Let us now try to understand our earlier made statements with the help of the reaction. Claisen-Schmidt condensation is a condensation reaction between an aromatic aldehyde that has no alpha hydrogen atom and an aliphatic aldehyde that has at least one alpha hydrogen atom in the presence of a base to form an aldol. The formed aldol now loses water in the step subsequent to it and forms an alpha beta unsaturated aldehyde. Alpha beta unsaturated aldehyde. Now in this reaction I have used the simplest of all aromatic aldehyde that has no alpha carbon atom. This is benzaldehyde. I have used an aliphatic aldehyde that has at least one alpha hydrogen atom. This is the simplest of it, acetaldehyde. I have reacted them both in the presence of dilute NaOH to form the aldol, the IUPAC name of which is 3-hydroxy-3-phenyl-propanone. The aldol formed now loses water in the step sequential to this to form the alpha beta unsaturated aldehyde, the IUPAC name of which is 3-phenyl-2-propenyl. Let us understand the second comment with the help of the reaction. This reaction, Claisen-Schmidt condensation, is a reaction between aromatic aldehyde and methyl ketone in the presence of a base to form a ketone. The formed ketone loses water subsequently to form alpha beta unsaturated ketone. In this reaction I have used the simplest of all aromatic aldehyde that has no alpha hydrogen atom, benzaldehyde. I have used the simplest of methyl ketone, acetone. Treated them both in the presence of dilute NaOH to form a ketone, the IUPAC name of which is 4-phenyl-4-hydroxy-2-butanone. The formed ketone loses water in the step sequential to this to form alpha beta unsaturated ketone, the IUPAC name of which is 4-phenyl-3-butene-2-one. To better understand the reaction, let us go through its mechanism. Let us now look at the mechanism of Claisen-Schmidt condensation. The mechanism is nucleophilic addition of enolate ion to the carbonyl carbon of aromatic aldehyde. There are 4 steps in this mechanism. Step number 1, Formation of enolate ion. The OH minus that dissociates from NaOH now attacks and knocks out a alpha hydrogen atom from aliphatic aldehyde, which is acetaldehyde in this case. When it knocks out a H from this molecule, it leaves its electron pair, resulting in the formation of an enolate ion. The dissociated H plus now combines with OH minus to form H2O. It is quite easy to knock out a H for an OH. As to know why it is easy, we have to scrutinize the structure of acetaldehyde or any aliphatic aldehyde. As you can see, this bond, the carbon double bond O bond here, is a highly polar one. This is because oxygen is electronegative, because of which the electron cloud is always towards oxygen, resulting in a negative sign over oxygen and a positive sign over carbon. The positively charged carbon is an electronegative one. It pulls electron from adjacent carbon, and the adjacent carbon pulls electron from the adjacent alpha hydrogens. Therefore, there is always a very small positive charge over all the alpha hydrogen atoms. It is at this juncture that OH minus intervenes. Sensing that OH minus has greater availability of electron, the H plus dissociates from this molecule. When it dissociates, it leaves its electron pair with the molecule, resulting in the formation of an enolate ion. The dissociated H plus goes and combines with OH minus to form an H2O. It is very appropriate here to state that OH minus won't knock out any alpha hydrogen atom from aromatic aldehyde, which is benzaldehyde in this case, simply because benzaldehyde doesn't have any alpha hydrogen to be knocked out. Therefore, it is always the enolate of the aliphatic aldehyde that is formed in the reaction. Step number 2. Attack of the enolate ion. The enolate ion which is formed now goes and attacks the carbonyl carbon of the aromatic aldehyde. As to know why it attacks the carbonyl carbon of the aromatic aldehyde, we have to analyze the structure of the aromatic aldehyde. The carbon double bond O here is a polar one. Oxygen, simply because it is more electronegative, the shared pair of electron is always towards oxygen, resulting in a negative sign over oxygen and a positive sign over carbon. The positively charged carbon now acts as a nucleophilic center. It is at this point that nucleophilic addition of the enolate ion to the carbonyl carbon of aromatic aldehyde takes place, and this results in the formation of this compound. Step number 3. Abstraction of proton from water. The water that is released in step number 1 is amphiprotic in nature. That means it acts as an acid when it encounters a strong base like this. This is a base because there is availability of electron, and because of this availability it can accept H plus. Because this compound can accept an H plus, it is a Lowry-Bronsted base, and because the H2O can donate an H plus, it's a Lowry-Bronsted acid. The dissociated H plus now goes and combines with the oxygen here, resulting in the formation of a mixed aldol. It is very pivotal here to note that OH minus is retained back now here in this step. The OH minus that was consumed here in step number 1 is retained in step number 3, therefore reinforcing the role of OH minus as a catalyst. Step number 4. Elimination of water. the mixed aldol that is formed is highly unstable. To know why it is unstable, we have to analyze the structure of mixed aldol. The mixed aldol here has a very polar bond, the carbon double bond O. Oxygen is electronegative and therefore it's negatively charged, and carbon is electropositive, it's positively charged. The electropositive carbon, the positively charged carbon, is electronegative in nature. It pulls electron towards itself from the adjacent carbon atom, and in turn the adjacent carbon atom, which is the alpha carbon atom, pulls electron from the alpha hydrogen atoms. Here the situation is something different. It has 6 sp2 hybridized carbon atom, the phenyl ring. Each of the sp2 hybridized carbon is electronegative. That is, there are 6 electronegative carbon atom, and that makes the phenyl group a -I group. That means the phenyl ring pulls electron from this carbon atom, and this carbon atom, the adjacent carbon atom, pulls electron from OH. However, oxygen is also electronegative and it also pulls electron towards itself. So this bond is a highly stressed one, and it's a matter of time that OH minus splits from the molecule. When the OH minus dissociates, a positive charge comes on this carbon atom. The positively charged carbon atom now attracts the nearest electron pair towards itself, that is nearest electron pair from the alpha carbon and alpha hydrogen. When this electron pair is pulled towards itself, H plus dissociates. The dissociated H plus now combines with OH minus to form water. The electron pair which is pulled now establishes itself as the second bond between alpha carbon and beta carbon, resulting in the formation of an alpha beta unsaturated aldehyde. There are 3 key movements in this reaction. Number 1 is the role of base as catalyst. As we can see, base was used in first step while it was retained in the third step. This reinforces the role of base as a catalyst. The second event is the formation of mixed aldol, and the third event is the elimination of a simple molecule of water, which makes this reaction a condensation reaction. Therefore, Claisen-Schmidt condensation is a base catalyzed mixed aldol condensation reaction between an aliphatic aldehyde that has at least one alpha hydrogen atom and an aromatic aldehyde that has no alpha hydrogen atom to yield an alpha beta unsaturated aldehyde. We will discuss other aspects of this reaction. Things to consider in a Claisen-Schmidt condensation: you can only use dilute NaOH. For if you have used concentrated NaOH, the concentrated base would break the pi bond between the carbon and the oxygen in an aromatic aldehyde, resulting in the aldehyde to undergo Cannizzaro reaction, which is a disproportional reaction wherein 50% of the aldehyde molecule is oxidized to an acid and 50% of the aldehyde molecule is reduced to an alcohol. In this case, have you had used concentrated NaOH, 50% of the benzaldehyde molecule would have been oxidized to benzoic acid and 50% of the benzaldehyde molecules would have been reduced to benzyl alcohol. However, you have used dilute NaOH in this reaction, and it is because of this the reaction proceeds as Claisen-Schmidt condensation. Another query that may pop up in the mind of a student is whether the enolate ion of an aliphatic aldehyde would go and attack the carbonyl carbon of an aliphatic aldehyde rather than the carbonyl carbon of an aromatic aldehyde to yield a crossed aldol. For students who have such a query, the answer is a big no. The enolate ion would only attack the carbonyl carbon of an aromatic aldehyde. It's simply because the carbonyl carbon of an aromatic aldehyde is more positive. In addition to the oxygen atom, which is a minus I group, the carbonyl carbon has another minus I group at the adjacent position, which is the phenyl group. Both these minus I groups greatly increases the positive charge on the carbonyl carbon of an aromatic aldehyde. Contrarily, in an aliphatic aldehyde, there is minus I group only at one position. The carbonyl carbon here has a plus I group at the adjacent position, which pumps its electron and reduces the positive charge on the carbonyl carbon, making it somewhat neutral. Now, because our enolate is a nucleophile, it would attack the more positively charged carbon atom, which in this case is the carbonyl carbon of the aromatic aldehyde, to yield a mixed aldol. Dear students, I hope you have liked and you have understood the class. If it is helpful for you, please do not forget to like, share and subscribe this channel. Thank you very much.